Welcome back, everybody. Today's lesson is on a topic that I really find interesting. Well, I find all this stuff interesting, but especially interesting. And that's adiabatic temperature change and the orographic effect. And you can see that actually taking place here in this wonderful picture. I call these the cloud hats here. These are some volcanoes in Africa. But these aren't clouds caused by volcanic eruptions. It's caused by adiabatic temperature change and the orographic effect. So let's learn some more about this. First, adiabatic temperature change. Changes in air pressure usually result in a change in air temperature. Sometimes this change in temperature is enough to cool the temperature to the dew point. And adiabatic temperature changes can be thought of as air temperature changes due to changes in air pressure. And that's simplified for this particular unit. There's more to it than that. But you can see in this diagram down here some parcels of air, and that parcel is expanding as it rises because there's less air pressure higher up in the troposphere than there is down at the ground. And you can see there's an effect on temperature because of that. Move forward here a little bit. Which box is at an altitude with the lowest air pressure? And if you answered the upper box, you're correct, and that's why it's expanding. You can think of the lower box as a box that has more energy concentrated in a smaller volume. And you can see the temperature there is 92 degrees Fahrenheit. The outside air pressure is pushing more on that, causing those air molecules to be in a smaller volume and therefore concentrating that energy around, so it's reading warmer. The upper box, however, is much cooler. The air's energy is more spread out there because there's less pressure around it holding it in, so it can move outwards and thus spread that energy around. So it reads a lower temperature, and the temperature there just happens to be at the dew point. And of course that means condensation is occurring and there's a cloud. Rising warm and moist air cools. How does it cool? And what happens when you cool water vapor? And you can see the air here represented by these little spheres. 32, then 22, then 12. Eventually it cools to the dew point. The condensation level is at 3,000 meters in this particular picture, and you get the cloud forming. Now a lot of that cloud is actually going to be ice crystals because it's way up high, -3 and -8 Celsius at 4 and 5,000 feet. But what you want to remember with all this, let's keep it simple here, when warm air rises, it expands and cools to the dew point. Condensation occurs, forming a cloud. If air sinks, the opposite happens. So whatever causes air to sink is going to cause it to compress and warm above the dew point, and the clouds will evaporate. So you can just remember rising, expanding, cooling air equals clouds, whereas sinking, compressing, and warming air causes no clouds. This is really important in weather, and I can't stress this enough. Anything causing air to rise is going to make clouds generally form. And if it rises faster, you get more violent cloud formation and possibly storms. Anything that causes air to sink is going to evaporate clouds and cause nicer weather. We can now see that the vertical movement of air, up or down, changes air pressure, which changes its temperature. This temperature change affects the relative humidity in the dew point, as we've learned in the past few lessons, and results in condensation or evaporation, kind of the opposite processes here. But what causes the vertical movements of air? Well, in meteorology, there's many things. Let's talk about 3. First of all, air currents warmed by the sun. We know that the sun heats the earth, and that warmer air is going to rise up. That's vertical movement. Second, weather fronts. We're going to see coming up how weather fronts can act like wedges, forcing air up and higher into the sky, causing this vertical movement. And the third thing that we'll discuss are mountains, which obviously the air can't go through the mountain, so it's going to go over the mountain. All right, let's focus first on the unequal heating by the sun. We see that in this particular picture. The sun is heating up the ground, the air is rising, and as it rises, it's expanding and cooling, forming this thunderstorm. Second, we see an approach of a cold front, and we can see the upper version, the top view of the cold front here. We'll learn more about fronts next week, but you can see these little shark's teeth here, I like to call them. That's that biting cold front, and it's moving this way. But that's the top view, and you really don't see what it's doing to the air until you look at the side view. And here is this cold air mass right here moving this way. And as it moves, it's hugging the ground because it's cold, dense air, forcing the relatively warmer air in front of it up and out of the way. And that rising air creates clouds, rising, expanding, and cooling. That's why you get thunderstorms at cold fronts on occasion. And the third thing that can lift this air up, of course, are mountains. And this is called the orographic effect. And what we can do here is we can drag this little slider, and you can see the air moving has to go over the mountain. It can't go through the mountain. And as it rises, it's forced to expand and cool to the dew point. And you get either rain or snow, depending on your elevation. And then when it sinks on the other side, a lot of that moisture has been removed from the air. And so now, as the air sinks, compresses, and warms, not only is it getting warmer, but there's less moisture in there, and that air actually will warm up quite a bit more than it was on the other side. So the windward side of the mountain is what we call the left side. The leeward side is the right side, and the right side tends to be warmer and drier. You might even get deserts if it's warm and dry enough, whereas the windward side is much more moist and cooler. And you'll see this especially out west with the Rocky Mountains and the Sierra Nevadas, the Cascades. The western sides, the western slopes are much more moist than the eastern slopes, and the eastern slopes are definitely warmer, drier and warmer, more desert-like. So air is forced to rise over the mountains and cools on the windward side and warms on the leeward side. They call that the rain shadow. Rain shadows on this far side over here. And there's just a diagram showing the same exact thing. That moist air is coming up off the ocean, rises on the windward side. It's going to snow on the windward side or rain, and the leeward side will be drier and warmer. Great examples out in the western United States, in the state of Washington, the Olympic Mountains. They have some orographic effect, as do the Cascade Mountains. And there's what I'm talking about. The air rising, expanding, and cooling there. The air rising, expanding, and cooling there. But on the leeward side, it's sinking, compressing, and warming. Sinking, compressing, and warming. And that creates drier conditions on the east side of the Olympic Mountains and on the east side of the Cascade Mountains. It's actually desert-like in the northern United States by Yakima and Spokane. You can ask me some stories about that on a bike trip I took a long time ago, and I'll give you examples, my personal experience. All right, this is the same picture here, my version of the picture. It's kind of a horrible picture. I'm going to skip right past this. And here you can actually see some of this orographic lifting and the air at the Rocky Mountains there being lifted and forming clouds on the windward side. It's kind of a cool shot, actually. Here's a typical regions question, or a couple of them, asking about this. On which side of the mountain and at which elevation is the relative humidity probably at 100%? And you can see there's some information in the picture which will give that away. First of all, you can see the dew point on the windward side of the mountain, 16 degrees. Leeward side, they don't really give you any information about dew point. And also relative humidity, 100%, we're talking rain here, we're talking clouds. So we know we're on the windward side for our answer. So we can cross off this one and this one. We got to look on the windward side. All right, now they want 100% relative humidity. So we have two choices here. Windward side at 1.5 kilometers and 0.5. And if we go to 0.5 kilometers, you'll see that there are no clouds. It's not raining. And we go to 1.5 kilometers, and we can see there's clouds and rain. So our best answer, we know it's at 100% on the windward side at 1.5 kilometers. Okay, the next question, how does the temperature of the air change as the air rises on the windward side of the mountain between sea level and 0.5 kilometers? So between sea level and 0.5 kilometers, we're at here, sea level, 0.5 kilometers you've already drawn right here, and the air is rising. we know that that air is going to rise, expand, and eventually cool to the dew point. And we want to find an answer that has something to do with rising, expanding, and cooling. So we know we can get rid of warming due to expansion. That's just not right at all. And warming due to compression. So we're looking for cooling due to expansion. And that is choice C. The map below shows the locations of 4 cities, A, B, C, and D, in the western United States, where prevailing winds are from the southwest. Which city most likely receives the least amount of average yearly precipitation? All right, we want to first remember the orographic effect is saying that the air is going to rise, since the winds are coming this direction, southwest towards the northeast. The air is going to rise, expand, and cool. And so the west side of the mountains, the windward side, is going to be wet. So it's going to be wet on this side of these mountains, and dry on the east side. Dry right here maybe, and dry maybe on this side. So things are looking like point A is probably the best answer. However, C and B, what's going on there? These are just cities located on the coast or near the coast. I would have to say, since they're kind of near the ocean and the winds are blowing off the ocean, that those are probably going to be more moist than this area where point A is located. So I'm going to go with point A. And you should too. And that is it. Hopefully you learned a little bit about the orographic effect and adiabatic temperature change.